Hello everyone, my name is Anh Nguyen and this is my video for the final project of the EMA 4003 course. In this video, I'll be covering the topic body-centered cubic crystal structure. Today, we're going to dive into an exciting topic in material science, like metallic crystal structures. Specifically, we'll be exploring the body-centered cubic structure and how to calculate the atomic packing factor for BCC. Before we dive into the specifics, let's start with a basic understanding of metallic crystal structure. Imagine that the atoms of a pure metal are packed together closely and are arranged in a very regular grid. Because of this regular structure, metal is what we call a crystalline material, and the grid that the atoms are arranged in is called the crystal lattice. We can think of a crystal lattice as a repeating number of identical units that we call the unit cell. There are minimal restrictions as to the number and position of nearest neighbor atoms in the structure. This leads to relatively large numbers of nearest neighbors and dense atomic packing for most metallic crystal structures. Some of the prominent properties of a metallic structure can be named like, first of all of the atoms in the structure have the same radius because they are usually of the single element. Another way to describe the bonding in metals is non-directional. That is, an atom's nearest neighbors surround it in every direction rather than in a few particular directions. Because the bonding is non-directional and coordination numbers are high, it is relatively easy to deform the coordination sphere, like break or stretch bonds. Another thing you can see is that because the atoms are densely packed, the distance between atoms is as small as possible in order to lower the bond energy. There are several different ways that the atoms can pack together, which means there are several different types of unit cell, and three relatively simple crystal structures are found for most of the common metals are face-centered cubic, body-centered cubic, and hexagonal close-packed. In today's video, I'll be focusing on the body-centered cubic structure. Now let's talk about one of the common crystal structures found in metals, the body-centered cubic structure, often abbreviated as BCC. This common metallic crystal structure has a cubic unit cell with atoms located at all 8 corners and a single atom at the cube center, as you can see in this picture. This is called a body-centered cubic BCC crystal structure. Atoms in this structure touch each other along the diagonal of the cube. For metals, each atom has the same number of nearest neighbor or touching atoms, which is the coordination number. For body-centered cubic structure, the coordination number is 8, which means each center atom has 8 nearest neighbors, corner atoms. Each BCC unit cell has 8 corner atoms and a single center atom, which is wholly contained within its cell. Therefore, the numbers of atoms per BCC unit cell is 1 center plus 8 corners multiplied by 1/8 equals 2 atoms per unit cell. Another thing to remember about BCC is the atomic packing factor, which is 0.68. Some examples of metals that have this structure are chrome, tantalum, and molybdenum. Now that we understand the basics of metallic crystal structures, let's move on to discuss atomic packing factor, or APF for short. APF is a measure of how efficiently atoms are packed within a crystal structure. It gives us insights into the density and stability of the material. To calculate the atomic packing factor of a body-centered cubic structure, you need to consider the arrangement of atoms within the unit cell and the ratio of the volume occupied by the atoms to the total volume of the unit cell. In a BCC structure, the total number of atoms per unit cell is 2, so we put 2 here. And the volume occupied by the atoms is calculated by considering the size of the atoms and their arrangement within the unit cell. For BCC structures, the relationship between the lattice parameter A here and the atomic radius r of the atoms can be expressed as 4r equals square root of 3a. To derive the relationship between the lattice parameter A and the atomic radius r in a BCC structure, we can consider the geometry of the structure. In a BCC structure, the atom at the center of the cube is in contact with the atoms at each of the 8 corners of the cube. This arrangement forms a diagonal of the cube, as you can see here. This diagonal can be calculated using the Pythagorean theorem in terms of the edge length A. In this picture, this is the diagonal of the cube, and these two square root of 2a is obtained by using the Pythagorean theorem for the triangle at the bottom of the cube. Or you can use the top of the cube also, but I'll use the bottom. So to find this diagonal, this h is a and this h is square root of 2a. By simple calculation, you'll get the diagonal equals to square root of 3a. In this picture, as you can see, since the diagonal goes past r, 2r, and r, so the diagonal is equal to 4r. And that's how we get the relationship between r and a. By using that relation, we can get r to find the volume occupied by the atoms. We know that the volume formula is 4/3 pi r cubed, so substitute r from the relation, we'll get this one. The volume of the BCC unit cell can be calculated using lattice parameter A, and the volume of the cube is A cube. So in result, the APF of BCC is 0.68. As we conclude our presentation today, I hope you've gained a deeper understanding of metallic crystal structures, particularly the body-centered cubic structure and the significance of atomic packing factor. These concepts are fundamental in material science and engineering, influencing the properties and behavior of metals in countless applications. And for the last part of this video, I'll show you a 3D model of the body-centered cubic structure. Let's take a closer look at the body-centered cubic structure with this 3D model. As mentioned earlier, in a BCC structure, each atom is surrounded by 8 neighboring atoms, as you can see here, forming a cube. What's unique about this structure is the additional atom positioned right at the center of the cube, hence the term body center. The central atoms adds stability to the structure and influences various material properties. Now, as we rotate the model here, observe how the atoms are arranged within the unit cell, creating this characteristic cubic lattice. This visual representation helps us better visualize and understand the arrangement of atoms in a BCC crystal structure, which is fundamental to the behavior of many metallic materials. So this one concludes my presentation on the body-centered cubic structure. Thank you for listening.